Hello, kiddos, and welcome to 16.2. We're going to look at a different definition of how to perceive an acid and a base. In Chem 20, in Science 10, I should say. In Science 10, we started to have an understanding of what an acid and a base was. In Chem 20, we're like, hey, listen, this is Arrhenius' theory. Now we're going to have a modified theory. And guess what? In Chem 30, there's yet another example or definition of what an acid and a base is. I know, it just gets better. So in Chem 30, we are going to learn about something called the Bronston-Lowry acid-base concept. And this definition of an acid and a base is going to rock your world. It's totally kind of kookaloo. Anyhow, what you need to know is that at first it's going to be a little bit like, oh, what? What's going on? But as you do it, you're going to see that it's fun. This is probably one of my favorite parts of this unit is just identifying the acid and comparing it to the base, et cetera, and what makes an acid and a base according to Bronston-Lowry. So let's just recap what we've learned so far in your chemistry career about what an acid and base is. So Arrhenius' theory, and this is Arrhenius here, looks so happy. I always find these scientist pictures, they're always not smiling. It's very strange. Acids ionize in water to produce hydrogen ions plus an anion. You remember that? It just ionizes. And it just looks like dissociation, but we call it ionizing because it's in an acid. There's no, and this is just, ionizing is going to make the assumption that it's just a dissolving, okay? We're not even thinking about reacting, it's just dissolving. He also said, hey, listen, bases dissociate in water to produce hydroxide ions plus a cation. And this, of course, only happens with bases that have the hydroxide ion concentration, the hydroxide ion in the actual chemical formula, okay? So it failed to predict the acidic or basic properties of some compounds, like ammonia, for example. Ammonia shows up as a base because it has a pH higher than 7, except there's no OH, right? So Arrhenius is like, dude, I think you're wrong because this is the data that we have, et cetera, et cetera. So then he modified his definition. So we have the modified Arrhenius theory. Acids are substances that react with water. So now instead of dissolving or ionizing, we have this word react. So it shows a chemical change. And it doesn't react to form hydrogen ions anymore. It reacts to form this cool thing called a hydronium ion, as you recall from Chem 20. Bases, he said, okay, I'm going to change my mind. I'm going to modify my definition, making it better. Bases are substances that react, here we have that word again, react, pretty cool, with water to produce hydroxide ions. Okay, here's our hydroxide ions. Let's just take a minute to look at what's happening when there's a reaction. When there's a reaction, this hydrogen here, and for an acid, is moving over to the water, and it's bringing with it a positive charge. That's where we get our extra hydrogen, and we have the positive charge from. For a base, notice it's moving in a different direction, and it's bringing that positive charge, right? And it's bringing that over so that you get your hydroxide as a product, but here we have our hydrogen, right? So it started off with NH3, now we have NH4, and we also have this proton, this positive charge because of the hydrogen. That's kind of cool. So there are some limitations to this as well. There's no provision for reactions that do not occur in aqueous solutions. Okay, awesome. So let's come up with another one, right? Some substances have both acidic and basic properties. Sodium bicarbonate, for example. These substances are called amphoteric. What does that mean? Amphoteric is a cool word. Amphoteric means that they act both as acids and bases. I know, right? How can something be both an acid and a base? That makes absolutely no sense. Well, we're not looking at acids and bases in terms of their empirical properties. Remember, empirical properties are, oh, like turns red, litmus blue, that kind of thing. We're looking at an acid and a base in Chem 30 in a completely different way. So are you guys ready for this? Okay. It's called the proton transfer concept. Proton transfer. There's a movement of protons from one substance to another, and that is it. If you can follow the movement of the proton, you can figure out where your acid is and where your base is. Now, definitely these are Bronston-Lowry acids and Bronston-Lowry bases. So it just different, it has a different quality to it than an actual acid and a base and how they act empirically. So the Bronston-Lowry concept does away with defining a substance as being an acid or a base. It is now an entity that is referred to as acting as an acid or acting as a base in the context of a specific reaction. So you're looking at a reactant and how it acts. Is it acting like an acid? Is it acting like a base in a particular reaction? Because that same substance in a different reaction can act totally different. A Bronston-Lowry acid is a proton donor. Okay, so here we go. An acid, according to Bronston-Lowry, is a proton donor. Okay, it donates protons. And a Bronston-Lowry base is a proton acceptor. It's accepting the proton. It's like, hey, I want the proton. I'm getting that extra positive charge. That is what we know as a Bronston-Lowry base. Okay. Okay, so Bronston-Lowry reaction involves a single proton transfer from one entity, the acid, to another, the base. Remember, one's donating, one's accepting. Here's an example. Hydrogen chloride in water is quantitative. Now, be very careful. When something's quantitative, remember, it has a high probability, like more than 99%, that it's going to form the hydronium ions. There's no two double arrows. It's just one arrow pointing towards the products because it's one of the 6. Hydrogen chloride, for example, HCl, is one of the 6 strong acids. So that's why you have just the arrow pointing in one direction. Okay, kiddos, very important. So you have HCl reacts with water to form your H3O plus your chloride ion. Let's take a look at ammonia and water. Now we have this double arrow, okay? That's not quantitative. The only quantitative things are your 6 strong acids. And if you take a look at your data booklets, I think it's page 8 and 9, you will notice, if you want, you can actually take a look at your data booklet right now. You'll notice this big honking table takes up 2 pages. I know, so much fun. And here, you'll see at the very top, there are 6 strong acids, and they're all quantitative. Okay, those are quantitative. One arrow pointing towards the products. Okay, anyways, I digress. If I take ammonia and I react it with water, look at what's happening to the hydrogen. It's here, okay, it's donating. This hydrogen here is donating a proton, and ammonia is accepting the proton, okay? So that is this movement of protons, the donating and the accepting of the proton is going to tell us if something is a Bronston-Lowry acid or something's a Bronston-Lowry base. So the acid is the donating of the proton, whereas the base is the accepting of the proton. There's your base, there's your acid, based only on who's donating the proton and who's accepting the proton. So water has ability to either accept or donate a proton, making it amphiprotic, okay? So water, as you can see here, water can act as a base and water can act as an acid depending on the equation. So it's there aren't many entities that can actually do both. Water is awesome because it can do both. Water is totally cool. It's no wonder God made so much water. Okay, right? Okay, so here we go. Water as an acid is donating the proton. Water as a base is accepting the proton. Other examples, here are some other examples of things that can be acting as an acid and a base. Okay, here's another example, hydrochloric and ammonia solution. In this case here, we're comparing what the acid and the base is due to what is going on in terms of who's donating and who's accepting. The base here, ammonia, is accepting the hydrogen ion or the proton. Think of it as a proton. So it's the base. If you take a look at ammonia gas and hydrogen chloride gas, ammonia, okay, as well in this case is accepting the proton, so it's a base in a different situation. Okay, so water does not have to be present in order for this to happen. Now this is another thing that's really important. The whole point of this last example is that it's not, doesn't always have to happen in solution. And that's why Bronston and Lowry, the definition of an acid and a base according to Bronston and Lowry is unique because it also shows the concept of something acting like an acid, acting like a base, based on the accepting or donating of the proton, and it doesn't have to be in solution. That's very key. It does not have to be in solution. The hydrogen carbonate ion is also amphiprotic. I have a problem with that word. I don't know. Because it can either accept a proton, as you can see, or it can donate a proton, as you can see. All right, kiddos? So kind of cool. Hydrogen carbonate ion it does both. And we have this cool word, amphiprotic. Say that 10 times. And I'm not very good at it. And I stutter sometimes, sorry. The presence of the hydrogen carbonate ion makes sodium bicarbonate, baking soda, an amphoteric substance. Now, oh my gosh, it's a different word. Okay, look at amphiprotic and amphoteric, right? It means the same thing. It's exactly the same thing. One acts like a verb and the other one acts like a noun. Okay, is this English class? Okay, it's not. However, no way, no how am I ever going to ask you the difference in a test. Those words are used interchangeably. Okay, just be aware. Okay, bicarbonate ions can raise the pH of a strong acidic solution. Okay, and it could lower the pH of a strong basic solution. So basically, you use it to help neutralize strong acids, and you actually can use it to neutralize bases. Good stuff, right? And you can use it to make to cook with. So baking soda is awesome, and you can use it in your fridge to get rid of smells. It's like the best substance ever. All right, so let's talk about what a conjugate acid, a conjugate base is. You did kind of get a little bit of this when you did Chem 20. Maybe your teacher talked a little bit about a conjugate acid, conjugate base. I do a little wee bit, but probably falls out of your brain, right? A Bronston-Lowry reaction results in an acid-base dynamic equilibrium where the forward and the reverse reactions occur at the same time and at the same rate. What the heck does this mean? Don't even sweat it. You're going to see how not difficult this is. Okay, so you have your acid and you have your base based on the fact one is donating the proton, one is accepting the proton. Your base here is you're accepting the proton, and your acid is donating the proton. All right, now let's take a look at what is going on in terms of how the reactants, how they compare to the products. In this case here, there's also a donation of donating and accepting of a proton. That's awesome that there's this side of this, but just think about this. If this is my acid, its partner, see how this side here is very similar to here, but it's on the other side, it's on the product side, it's on the opposite side, it becomes your conjugate base. And they kind of become a partnership. Here we have water, and it changed to the hydronium ion, right? So here's my base, and its partner is called a conjugate acid. So just be aware of those names. A pair of substances that differ only by a proton. So that's how they differ when you compare this guy to this guy. There's just a difference of one proton. Same thing with the H2O and the H3O plus. We call those conjugate acid-base pairs. Okay, so here's our conjugate. There's always two sets of conjugate pairs. There's your acid plus your conjugate base, and your base plus your conjugate acid. Each of those are partners or conjugate pairs. All right, so in your data booklet, look at this awesome table that encompasses 2 pages. Let's talk about this for a little while longer. Because this becomes super important when you are trying to figure out or you're predicting equations. I know you're going to be predicting equations again, just like you did with your electro, but this time you're doing it with acids and bases. So the first 6 here, these first 6, those are super strong. They're actually called strong acids. They're the only actual strong acids. Everything underneath them, they're considered weak acids. You can still have a strong-ish weak acid, but the term weak acid still applies, okay? So those 6, they're quantitative acids. They're strong acids. They react more than 99% of the time to form hydronium ions, and you only have the arrow pointing towards the products, okay? Acid strength. So as you move up this table, acids get stronger. So here is your weakest acid at the very bottom, and at the very top of your weak acids, this is your strongest. These are all kind of equal in terms of strength, and they're quantitative, so that you can't really compare them because they act differently. For your base strength is opposite. Bases increase as you go down. So this is your strong, okay, all right, whatever. The very bottom one, OH minus, is your strongest base, and this is your weakest base, okay? Your Ka values, which we'll talk about next time, so don't worry about it. Ka values decrease as you move down the table. That becomes important later. Alrighty, so here we go. Another thing that's really important, acetic acid has a strong attraction to its own proton. Doesn't donate it very easily, so it's a weak acid. Its conjugate base, the acetate ion, is a stronger base than water. It has a greater attraction for protons. So what do we get out of this kind of thing? The weaker an acid, the stronger its conjugate base. This is really important. This is like a acid-base commandment, if I should use that word. I don't know if I'm being disrespectful, but it's very, very important. The weaker the acid, the stronger its conjugate base. Sound good, kiddos? So here's an example. A hydrogen chloride molecule has a much weaker attraction for its own proton than water. This makes hydrochloric acid a strong acid. The stronger an acid, the less it attracts its own proton, and the stronger a base, the more it attracts another proton. So another example of another really important concept or phrase that becomes super important: the stronger an acid, the weaker its conjugate base. So kind of think of it as an inverse relationship between the acid and its conjugate base, okay? So a weak acid has a strong conjugate base. A strong acid has a weak conjugate base. Make sense, kiddos? Something that you have to memorize. Let's summarize really quickly, and then we'll move on to part 2. So an acid is a proton donor, and a base is a proton acceptor, and that changes. It all depends on the reaction. An acid-base reaction involves a single proton transfer from one entity, the acid, to another, the base. Okay, same kind of thing. An amphiprotic entity, which includes an amphoteric substance, is one that acts as a Bronston-Lowry acid in some reactions and as a Bronston-Lowry base in other reactions. Cool. A conjugate acid-base pair consists of two entities with formulas that only differ by one proton, right? Only one proton separates them. A strong acid has a very weak attraction for protons. A strong base has a very strong attraction for protons. The stronger an acid, the more weakly it holds onto its proton. The stronger the base, the more it attracts another proton. Oh my gosh, tongue twister. The stronger an acid, the weaker its conjugate base, and the stronger a base, the weaker its conjugate acid. Sound good? All right, let's move on to the next part. There's some homework if you want to do it for fun. I don't know, it's up to you. Predicting. Okay, this is really important. I'm going to go through a few examples, and I apologize about the lengthiness of this podcast, but it has to be done. In a system that contains several different possible acid-base reactions, the only significant reaction, does this sound familiar? In this case, when we're talking about acid-base, is a proton transfer from the strongest acid present to the strongest base present. So that's why we're going to use that data, our data booklets on page 8 and 9, and we're going to look for all acids, all your bases. You're going to identify them, including those that are both acids and bases, right? So water, for example, is going to show up as an acid and a base. Then you're going to find you're going to identify all the acids, all the bases, even though those substances that act as both. Then after all of that, you're going to identify your strongest acid, which is at the highest on the left-hand side, and you're going to identify your strongest base, which is at the bottom of your table on the right-hand side. Once you have those two, your reactants, kiddos, what you have to do is you have to be able to predict your products. Think about what is donating, what is donating, what is accepting in terms of proton movement or proton transfer. Do that, and then you'll be able to predict your products. Your products then are going to be the conjugate acid and conjugate base, and then you're going to have your conjugate acid and conjugate base pairs. Oh my gosh, I'm so sorry. I talked a lot there. Okay, So you're going to look, you're going to compare, and you're going to put together your strongest acid and your strongest base. For an aqueous solution system, we represent all entities as they exist in solution. So for strong electrolytes, we write in dissociated form. So what are strong electrolytes? Things like ionic solids, strong acids, and strong bases. And what we do for that is we write them in its dissociated form. However, weak electrolytes, we write as is, as they are. We don't break them down. We don't dissociate or ionize or anything like that. Okay, and there's an example right out of your textbook of the strong acids we write, or strong acids, strong bases, we write in their ion entity form. And for weak acids or weak bases, we write them as they are. Okay, steps for predicting the predominant acid-base reaction, then I'll go over some examples. Okay, kiddos? List all the entities as they appear in solution, including water. So list them all first, and then label those entities as acids or bases. After you labeled all of them, and you're going to mark them up, and use those little sticky pads if you have them. Label the strongest acid, your SA, look familiar, and your strongest base, your SB, using the table on pages 8 and 9 in your data booklet. Write an equation showing the transfer of one proton from the strongest acid to the strongest base, with the products being the conjugate base and the conjugate acid of their reactant. So you are actually going to predict the products. Number 5 is the most important, kiddos. Muy importante. Okay? Predict the position of the equilibrium based on the fact that the side that is opposite the strongest acid is favored. So you're either going to look at the strongest acid and pick the other side, or you're going to pick the side of the weakest acid. Okay, I know it's kind of like what, but you'll see. And more than either your products are going to be favored or your reactants are going to be favored, depending on if you're depending on where your strongest acid is. Now, when you're predicting your products, right, there's your conjugate acid and your conjugate base. Compare your acid and your conjugate acid. So the acid is going to be on your reactant side. The conjugate acid is going to be on the product side. Compare those two. Where the highest acid is between those two, it favors the opposite side of that, right? I know, it's kind of like not very intuitive, but we're going to work through some problems. Okay, what will be the predominant reaction of spilled drain cleaner sodium hydroxide solution is neutralized with vinegar? Vinegar is a weak acid, right? As reactants or products favored in this reaction. So you're going to name everything. Now remember, strong acids and strong bases dissociate. So there's your strong base, your sodium hydroxide, has to be written as sodium ion and hydroxide ion. Your vinegar or acetic acid is weak, so you have to actually write it as acetic acid. And you always include water because we're talking about vinegar, which is the solution, okay? And it says solution, so if it says solution, you have to include water. So then once you've listed all those out, sodium, you're not going to find it in that table on page 8 and 9 because it's metal ions and it's a spectator ion, so it's not really a thing. Identify things as acids or bases. Then out of all those things, find your strongest acid and your strongest base. Then you put those two together. Those are your reactants. Make sure that you are moving the proton over from the donator to the acceptor, and then you get your product. So you're actually going to predict what the products are based on the movement of protons. After that, you are going to decide, oh, let me go back. Oops, let me go back. Sorry, I apologize. I can't go back, but I'll show you what I meant with this. You're going to compare your strongest acid and between the acid and the conjugate acid, and then depending on that, you're going to decide whether the reactants are favored or whether the products are favored. But there is an example where it shows that, so don't worry about it if you missed it. Okay, ammonium nitrate fertilizer is produced by the quantitative reaction of aqueous ammonia with nitric acid. Write a balanced acid-base equilibrium equation. Okay, very tricky. If it's quantitative, kiddos, there's no real equilibrium equation. Quantitative, and it's also including a very strong acid, which is, where is it? Nitric acid, I thought I read. Yeah, nitric acid is one of the 6 at the very top. So, really, what you're doing here is you're just simply showing the one arrow, And your H3O, this is what represents your nitric acid. So you have your ammonia, which is your weak base, right? Reacts with your strong acid. Because it's reacting with nitric acid, which is one of the strongest acid, it actually ionizes because it breaks down to H3O, your hydronium ion, more than 99% of the time. And then you have your arrow that only points towards the products. Okay, it's quantitative. All right, so write the balanced acid-base equilibrium equation when aqueous potassium hydrogen carbonate is mixed with aqueous sodium hydrogen phosphate. All right, let's write all our entities down. Once we've written all the species or the entities down, potassium and sodium, they're kind of not a thing. Decide if they're acids or bases. Oh, look, they're all acids and bases. Out of all those, figure out what your strongest acid is and your strongest base is. Those two guys come together, right, as your reactants. So here's your acid, right, and here's your base. Because this is your acid, this becomes your conjugate base. Because this is your base, this becomes your conjugate acid, right? When you're comparing, or when you're deciding if it's going to favor the products or favor the reactants, compare these two. You have to compare this guy with this guy. Once you compare these two, whichever is higher on that table, right, that becomes your strongest acid, and it always favors the side that is opposite your strongest acid. Okay, so it's strongest acid, so the reactants are favored, right? So it's going to, the reactants are favored, the reactants are favored because this is your strongest acid between the two, right? Between this acid and this acid, this is your strongest one, so it's going to favor the reactants. And this little guy says less than 50%, right? Which means less than 50% is going to favor products. So in a way, it's oppositely kind of telling you it's favoring the reactants. I know, I'm so sorry. Chemistry is like, sometimes it's, I love it. Chemistry is so awesome, but sometimes it's counterintuitive. Yet another example, kiddos. Write the balanced acid-base equilibrium equation when perchloric acid HClO4AQ is mixed with aqueous calcium hydroxide. All right, so we have perchloric acid is one of the 6 strong acids, so it forms H3O, right? Because it has more than 99% of the chance it's going to form hydronium ions. We're going to dissociate the calcium hydroxide into its ions, and we're also going to include water because water is in solution. And you are going to identify your acids and bases. You're going to then identify your strongest acid, strongest base, put those babies together, and then figure out what is being formed. Obviously, 2 water molecules, so you can actually put, oops, I can't go back, 2 H2O, okay? That's all that means. All right, and this all of a sudden makes more sense. So that's all I have. A whole other definition of what an acid and a base is. And my apologies again for the length of this podcast. It's just that I had to just give you a lot of examples. Have a wonderful day, kiddos.